saints in lockstep.
Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course. So this is an attractive force caused by the electrostatic attraction of a hydrogen atom with a lone pair of electrons on another atom. Now this is a strong force as well, and we have to consider a couple of structural requirements to see whether molecules are capable of forming hydrogen bonds. First off, the hydrogen must have a sufficiently large partial positive charge. And because this is electrostatic, the other atom with which it is binding must have a source of electrons with which to do so. One of the most common examples of this is in water. So in water you have a rather large partial positive charge on the hydrogen atoms due to this bond dipole. Likewise, the lone pairs on oxygen of another molecule can be attracted to the hydrogen of another water molecule. So redrawn, it might look something like this. Now typically what we say is that in a hydrogen bond we have a hydrogen bond donor and a hydrogen bond acceptor. So the hydrogen bond donor has to have a sufficiently large positive charge on the hydrogen that's caused by its binding to a highly electronegative element such as oxygen, nitrogen, fluorine. So in the case of water we have hydrogen bound covalently to oxygen. The hydrogen bond acceptor is the one that has the lone pair of electrons. It has to have sufficiently high electron density, or the accepting atom must have a negative formal charge, or if it's neutral, it basically has to be oxygen or nitrogen. Now in hydrogen bonding there are still dipole-dipole moments. However, the hydrogen bonding is still the strongest force compared to dipole-dipole. Remember, that's a medium force. And so we say that that's given priority. The next type of force is the London force. So this is a noncovalent attractive force caused by polarized electron clouds between two different molecules. So when atoms or molecules approach each other, their electron clouds are distorted by random fluctuations and or by mutual polarization. And because of this, electrons repel. One electron cloud shifts slightly away from the other electron cloud, creating a small and temporary partial positive charge on one of the electron clouds. So the electron cloud of the second molecule is attracted towards this partial positive charge, resulting in a small and temporary shift of electron density and a partial negative charge within the other electron cloud. So what we have here is then the electrostatic attraction between the partial negative region and partial positive region of these two atoms or molecules. So this is an electrostatic interaction, however it is a very weak force. And the main factors that influence the strength of this interaction are the polarizability and what's called the molecular surface area of a molecule. Now let's go into a little bit detail what this means. So polarizability is the ability to distort that electron cloud. If the distortion is easy, we say that the species is soft. If it's more difficult, we say that it's hard. The question is then, what controls polarizability? And so I have here listed a chart of the different noble gases going down the column of the periodic table. Also their boiling points and atomic radiuses. So the boiling points are in degrees Celsius, the atomic radii are in angstroms. Now the larger the atomic radius, the softer the species is. And so soft again means that the distortion is easier, therefore more polarizable. Another thing to consider is the electronegativity of each one of these atoms. So the larger the electronegativity, the harder it is. Harder, again, meaning less polarizable. Therefore, we can derive a trend here to explain this trend of decreasing boiling point. So as you go down this column, you have an increasing attraction between different atoms of these noble gases. You also have increasing ease of electron cloud distortion, right? So increasing atomic radius from top to bottom means increasing the softness or ease of polarizability of their electron clouds. So the attractive London force between these atoms is going to be stronger. In doing so, you are raising the boiling point. Now, another thing that you must consider when looking at London forces is what's called surface area effect. So the increasing of a molecule's surface area will increase the London attractive forces between them. So what we can do is compare molecules that have the same polarizability but different surface areas. So if we look at CH4, CH3, CH3, and CH3, CH2, CH3, or methane, ethane, and propane, these compounds have boiling points of negative 162 degrees Celsius, negative 88, and negative 42. So this clearly shows an increase in the boiling point with an increasing surface area of these molecules. They all have very similar to polarizabilities, and that's because hydrogens are very, very small atomic radii, meaning that they're hard and very low, have very low polarizability. And we can see then with the surface area of each one of these molecules, increasing surface area leads to increasing boiling point, and therefore increasing London force attraction between molecules. Now, one other thing to consider here, though, is the molecular weight of these compounds. So they also increase from 16 to 30 to 44. And so this might lead one to question whether this is just a molecular weight effect or if it's actually a surface area effect. But what you find is that this doesn't really matter too much. And so if you compare compounds that have the same polarizability, the same molecular weight, but different surface area, you will still find a difference in the boiling points of those compounds, which can only then be related to the surface area effect.